Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem. Check if there is a valid partition for the array. We're given an integer array nums, and we have to partition it into one or more contiguous subarrays. And the catch here is that each of the subarrays has to be considered valid, where this is our criteria to check if that subarray is valid. And there are three types of valid subarrays. The first one is where the length is exactly 2 and each element is equal in the array. So in this example, they show us 2, 2. Alternatively, it could be 3, 3 or 4, 4. Basically, it's length 2 and both values are equal. So first thing that you might notice is that's pretty simple to check. Like, we don't need a loop to check that. That's something we can literally check with an if statement. So let's take a look at the other two cases as well. The second case is where the subarray is exactly of length 3. And the example they show us is 4, 4, 4, and you can imagine it can be 5, 5, 5. Basically, length 3, all values are equal. Now, that's also pretty simple. I mean, we can do that again with an if statement. It might be a kind of long if statement, but it's still doable. I'd rather not use a loop if we don't have to. It's not like the length of the subarray is a variable length. It's always going to be 3 in this case. Last case, it's also going to be exactly of length 3. This one is a bit more complicated though. Each value in the subarray, for example, 3, 4, 5, has to be in increasing order, not just in increasing order. A subarray like 1, 3, 5, this is not considered valid because they have to be incremented by 1 each time. So a subarray like 1, 2, 3 would be valid. 1, 2, 4 would not, because each value has to be incremented by 1 in the sequence. So once again, this is pretty simple. We can actually check this with an if statement as well. We can check that the left value is exactly less than the middle value and that the right value is exactly 1 plus the middle value. Now, when it comes to solving this problem, the first thing that you might try is the brute force, like trying it recursively, because there's not going to be an easy way to determine, like a greedy way to split this up, because there could be multiple ways, and that's kind of obvious from the first example, because we could take this. I'll actually draw it out. So here we could take this as the first valid subarray, but we could also take this as the first valid subarray. So that gets my brain thinking that we can kind of have a decision tree. We can solve this recursively. We have choices that we can make. So one choice could be 4, 4. Another choice would be 3 4s. Now, all we want to know is, can we split this up such that every single subarray is valid? So we're either going to return true or false. So we're going to be exhaustive here. We want to explore every possibility. So here, how many choices do we have? Well, we're kind of at this position. That kind of tells us we should probably maintain an I pointer telling us where we are, because in this case, we went 2 spots and now we're here. But over here, we went 3 spots and now we're at the 5. So when we're here, we can check 3 different ways. We can check, are these 2 values equal? Nope. Then we'll check the second case. Are these 3 values equal? Nope. Then we check the last case. Are these 3 values in ascending order where each is being incremented by 1? Yep, that's the case. And at that point, we select 4, 5, 6, and then our I pointer will be all the way over here outside of the array. And since we're only choosing valid subarrays as we shift our I pointer, we know by the time that it's out of bounds, we have found a valid solution. We found a valid partition. And at that point, we can go ahead and return true. Now, just to explore this other side really quickly, when our I pointer is over here, we don't have many choices actually. We can only make the first choice. We can only check, are these 2 values equal? And they're not. And the reason we can only check that is, of course, because there aren't 3 values here to check. If we tried to check if all 3 values were equal, we'd get an out of bounds error. And same with this other case, if we check if the 3 values are ascending, we'd get an out of bounds error. So this path did not lead us to a valid solution. From here, we would actually return false. Now, just because we solved the problem recursively doesn't mean we found an efficient solution, but you can imagine that there are subproblems. They're going to be repeated subproblems. We don't care. Like if our I pointer got to this point, we don't care how we partition the array. There could be 10 different ways that we partition the array. Like imagine we had a bunch more values here. It doesn't really matter to us. This subproblem is the same regardless of how we partition these values. This leads me to think that we can solve this problem with caching, a dynamic programming technique, where the only cache key that we will have is the index, which defines the subproblem that we're currently looking at. It could be here, it could be over here, which defines this subproblem. It could even be at the first index, which defines the entire problem. And of course, each I index will be mapped to a true or false value. And the number of subproblems that we have in this case is of course going to be the length of the input array, which is big O of n. And each subproblem actually, like I said, since these subarrays are of length 2 or length 3, we're not going to need a variable while loop inside of our recursive function. Therefore, each subproblem is basically going to be an O of 1 operation, and that's why I'm getting big O of n as the time complexity, because there's n subproblems. Each one is going to be a constant time problem. Therefore, big O of n. Also, memory complexity is going to be big O of n from the DP cache. I'll quickly code up this solution, but I also want to show you the more memory optimized solution. It's the bottom up DP solution. It's going to be big O of n time and big O of 1 space, but that's going to be later. Let's jump into the recursive solution now. So the first thing I'm going to do is define the recursive function. I'm going to call it DFS because why not? And we're just going to have a single variable I. And like I said, the main base case is going to be if I is out of bounds, therefore it's going to be length of nums. And in that case, we're going to return true because we were able to split it up. Now I'm going to quickly show you how we're going to call our DFS. We're going to start at index 0. So that's going to inform how we implement the rest of the problem because we're starting at the beginning of the subarray. So now there's a couple cases, remember. One is we're checking two adjacent values. So we're checking is nums of I equal to nums of I plus 1. But before we even check that, we don't want to get an out of bounds error. So let's make sure that we have two values in the first place. We know that if our I pointer is less than the length of nums, well, this tells us we have one value, at least one value. Now, if this is less than the length of nums minus 1, then we have at least two values. So we want both of these to be true, and I'm checking this first so we don't get an out of bounds error when we try to evaluate this part. Now, if this does evaluate to true, that doesn't mean we found a solution. Now we have to solve the subproblem. So we have to call DFS again. What do you think we're passing in? Well, we probably want to shift our I pointer 2 times, so I'm going to pass an I plus 2. And this is what we would want to return. But there are some other possibilities as well. For example, if 3 adjacent values are equal, and that would look pretty similar like this. So now we're checking that, but just like before, we want to make sure we have at least 3 values. So I'm going to copy and paste that. And now I'm going to set it to minus 2, which guarantees that there are at least 3 values. And if we do that, we're going to call DFS on I plus 3. Now I'm going to copy and paste this because we know there's one more case, and that case is similar because we need to check 3 adjacent values, but we're not going to check them like this. We don't want to know if they're exactly equal. We want to know if they're in ascending order. So we want to know that the middle value is equal to the left value plus 1, and we want to know that the middle value is equal to the right value minus 1, so we can do that just like this. Now, there's actually an issue with this code. Just because this happens to be true doesn't mean we want to return the return value. I mean, if the return value here is true, that's great because all we need is one valid partition and then we can return true. But if this were to return false, we don't want to necessarily return false. We might want to explore these two possibilities as well. Basically, we have a recursive function here that is not branching at all. That's a problem. So instead of returning each time we call a recursive function, I'm actually going to have a variable over here, and I'm going to call it result, and I'm initially going to set it to false, and that's going to be the value that we return out here. Not false, we're returning the variable. So that's one improvement. But this is still not correct. We want to now take result and set it equal to the return value of this function. And also, we want to combine these two cases as well. The first thing that's common between them is that we're checking that the length is at least 3. We probably don't need to have this in both places, at least not the way I want to write it. So I'm actually going to have an inner if statement here. And you can also see, by the way, that the recursive call is the same for both of these cases. So we probably don't need to call it twice. That's another reason why I'm combining these. So I'm going to cut this condition up here and paste it down here. So either this is true or this condition down here is true. If either of these is true, then we're going to execute this DFS. So now I'm going to clean this part up. So now you can see we're checking is the length 3, and are either of these true? And if they are, then we call this, but we don't want to return it necessarily. We're going to set result equal to either whatever it currently is or the return value of this. Reason being, if this returns false, but this returned true, that doesn't mean we want to set this to false. If any of these return true, we want to return true as the result. Now, the last thing that we have to do is add caching, and I'm going to do that with a hash map. You can do that with a one-dimensional array. So here we add an if statement. We check, have we solved this subproblem before? Is I in our DP cache? If it is, that means we solved the subproblem, and we can immediately return, and we don't have to do any recursion down here. But if that's not the case, then before we return our result down here, we want to make sure we cache the value in our DP cache at index I, just like this. And now we're almost done. Actually, I see an issue here. We are missing a colon in our if statement, and this should be indented. Whoops, let me go ahead and indent that because it has to belong to the if statement scope. So now let's go ahead and run the code to make sure that it works. And as you can see on the left, yes, it does, and it's pretty efficient, but there is an optimization that we can make. So we talked about how we solved it recursively, and what we were kind of doing implicitly was building up a one-dimensional array. Well, in my case, I was using a hash map, but basically this is the structure that we were building up. We started at the beginning of the array, and that was the solution. Like, this is where we store the true or false value, whether we can partition this array successfully. But we also solved subproblems, meaning like at this position, this defines this subproblem, and here we can partition this. It follows case number 3. So here we would put a true value because we are able to partition this successfully. Now, the bottom up DP solution, in my case, following like the way I solved this recursively, I'm going to fill up this array from right to left. You could also do it from left to right, but then it's going to end up different from the recursive solution that we implemented. So that's why I prefer doing it from right to left. But if it bothers you, you can always do it the other way. But in my opinion, that actually ends up being more confusing, at least for me. Before I start like at the end of the array and start solving subproblems, we should probably just initialize the last 3 values first. Because first of all, we know that the last value, if it's just a value of length 1, then we have to put false here because there's no way to partition that successfully. And for the last 2 values, it's pretty easy to check. Just check, are these 2 values equal? In this case, they're not. So again, I'm going to put a false here. Now, for the last 3 values, they're not equal, but they are in ascending order. So here, I'm actually going to put a true value. Now, we can start filling up this array from right to left. It's a pretty short array, but we'll still get a pretty clear picture of how to solve this problem in the general case. And that is, so now our I pointer is going to be over here, which is basically the last index minus 3 because we already filled up these 3. So here we know that there's 3 different ways that we could partition this array. We could take these 2 values, and if they are equal, then we're going to take the value that's stored here and then put it there, because if we can partition this like this, then we want to know, are we able to partition the rest of the array starting at this value? And this is where we store the result of that. But clearly this is false. So we can put false here for now, but also let's ask ourselves, what about these three values? Are these three values equal? Nope, they're not. Okay, well, are these three values in ascending order? Again, no, they're not. If either of those statements were true, then what we could do is take the value stored here and then move it over there, but they're not, so we can't do that. Now we're going to put a false over here. And now we're going to shift our I pointer to the left by 1 and try to solve the entire problem here. So we're going to ask the same question. Are these two equal? Yes, they are. So then we're going to try solving this sub problem. And clearly there's a true here. So at that point, we're pretty much done with the problem. Now, the other cases we would have checked is, are these three equal or are these three in ascending order? Well, they're equal. So what we could do is take the value stored here. It's a false anyway. So we don't care about that false, but we know we were able to partition it like this and grab the true from here and then move it there. So ultimately the result of this problem is going to be true. But there might be a thing that you noticed. Every time our I pointer is in any particular position, we don't really need the entire array in memory, do we? Because there's only two cases. Either we partition the array like this, in which case we would want the value stored over here. Or we can partition the array like this, in which case we'd want the value stored at I plus 3. Basically, what I'm getting at is we only need 3 values in our array in memory at a time. That's how we make the memory optimization from big O of n down to big O of 1. So that's how I'm going to solve this problem now. So I'm going to leave this recursive solution here because we're actually going to use some pretty similar logic, at least for like this portion of it. The first thing I'm going to do is check if the last 2 values in our array are equal, because what we're ultimately trying to do is build up a DP array of length 3, and for each position, we want to fill in the slot. We already know that the last value is going to be false because an array of length 1 can't be partitioned, but we want to know, are the last 2 values partitionable? And we know that's the case if the last 2 values are equal. In Python, it's pretty easy. We can take -1, that's going to give us the last value, and we can take nums of -2, that's going to give us the second to last value. Now there's one edge case. Our nums array actually could be exactly of length 2. If that's the case, we can check that like this: is the length of nums equal to 2? If it is, we can return the value that we just computed in this variable. If that's not the case, then we pretty much know that the array has at least 3 values in it, and that's where we can go ahead and pretty much copy and paste this code. Well, not exactly, because we're going to have to shift it around. Well, not shift it, but we're going to have to update this I pointer. We want to check if the last 3 values are equal, so we can check that like this: -1, -2, and -3. Either that or the last 3 values are in ascending order. We can do that by changing this to -3. This will be the value to the left of the middle element. The middle element will be at index -2, and the last element will be at index -1. So now we can take these 2 variables and put them into our DP array just like this. So now let's start looping. We're going to start at the last index -3. So I in range length of nums -4. The reason it's -4 is because -1 is the last element in the array, and we want to shift that by 3. So we put -4. And we want to iterate in reverse order. In Python, it's kind of weird, but we have to put a -1 here. That will iterate until we reach the beginning of the array, and we want to decrement our pointer, so then we put a -1 there as well. And by the time we're done with this loop, we want to return the first value stored in our DP array, because that's going to be the result of the entire problem. Like, can we partition from the beginning of the array? So we're going to return DP at index 0. Okay, now this part is actually going to be pretty easy. We want to know, are we able to partition taking the first 2 values? So we can check that pretty easily. Is nums of I equal to nums of I plus 1? So this is pretty similar to what we did up above. except now we actually have like a pointer and we're not just hard coding it. And I think if you really wanted to, you could rewrite this code such that we don't even have these. You could start our I pointer, I believe, from like the end of the array, and then you could kind of just move these inside. But I think it's a bit more simple to just write it out like this. This is actually not enough for this problem, remember? We want this to be true, and we want DP at index 1 to also have a true value. Why DP at index 1? Well, that's gonna be us shifting by 1 and then shifting by 2. So that's a possibility. The second possibility is, and this is the part where we're now gonna say current or this condition, because it could be possible that current is already true now. So here, we're gonna copy the code from down here in our recursive case. So I'm literally just gonna copy and paste it. I'm gonna move it here. I think we're gonna have to update it a tiny bit. So we're asking either the current 3 values are equal or the current 3 values are in ascending order. But that alone is not enough. Remember, we want this to be true, and we want DP at index 2 to also be true. And again, the reason why it's DP at index 2 is because we want to shift our I pointer by 3. So we'd say 1, 2, 3, and we'd get the value that's stored there. Now, after we've computed that, we can actually just put current into our DP cache. But it's not going to be as simple as just saying DP at index 0 is going to be equal to current, because remember, we kind of have to shift that window over to the left. So actually, we're going to be reassigning this entire array. That's okay because it's only of length 3. So we're actually going to now set it to current is going to go in the first spot, DP of 0 is going to go in the second spot, and then DP of 1 is going to go in the last spot. So you can imagine we're basically taking these two values and then shifting them over by 1 so that they're here. We're literally taking these two values and then shifting them to the right by 1. And then for the first value, we're taking the value that we just computed and storing it there. So this is the entire code. It's memory optimized. Let's run it to make sure that it works. And as you can see on the left, yes, it does. And it's about as efficient, I think. I guess comparing the memory down here, it does look like we used a lot less memory. So if you found this helpful, please like and subscribe. If you're preparing for coding interviews, check out leetcode.io. Thanks for watching, and I'll see you soon.